Number 4, continuity on an interval. So far we did continuity at a point. So for that, we need limit x approaches to c, f of x equals to f of c. To say f is continuous at c, limit from the both sides should be equal to its function value. But continuity on an interval is a different concept. So in the beginning of the class, we said the interval is one connected piece. So it may include endpoints, or it can be one open, one closed, like this. Or closed here, open there, right? So function f is said to be continuous on an interval. Continuous on an interval if. So basically, if the point is inside, then we take the limits from both sides. If it is an endpoint, which is included in the interval, then we only take the limit from the left-hand side. And if the left endpoint is included in the interval, then we take the limit only from the right-hand side. So you're going to think there is nothing on the outside. My universe is only this interval. So you will assume that there are no points other than what is in the interval. So you're taking the limits only from the inside of the interval. That's the basic idea. Okay, so let's fill in the blanks. F is continuous at every point that is not an endpoint. So for points inside, you're going to take the limit from both sides of C so that it is continuous at C. Continuous at every point that is not an endpoint. But for the endpoints, you only take the limit from the points lying inside of the interval. So f is continuous from the right at the left endpoint. So that is this. Continuous from the right. So you're taking the limit only from the right of the endpoint, left endpoint of the interval, if that point is included in the interval. So that is that case. The remaining case is this. If f is continuous from the left at the right endpoint of the interval, if that point is included in the interval. Okay, so the bottom line is, if f is defined on an interval, then you're going to take the limit only from the points coming from the interval. Okay, so you're going to assume that there is no points outside. They are not my concern. So for example, f of x equals to 1 over x is continuous on the interval. So if I look at 1 over x, it is this and that, and that's 0. So for all c, we can take the limit from both sides, and that 0 is not in the domain, so it is open right there. Same thing with c on the left hand side, we can take the limit from both. So we can say on the interval, 1 over x is continuous on the interval, open 0 infinity, or minus infinity, 0. 6. True or false, justify your answer. So you're going to see such problems on the exam, right? F of x equal to square root of x is continuous on the interval 0, 1. So the graph of square root of x is this. Square root of x. So f of x is not continuous at 0. At 0, because we cannot take the limit from both sides of 0. There is nothing on the left hand side. But when we say f continuous on the interval 0, 1, at 0, we only take the limit from the right, and that is equals to the function value. So f is continuous from the right at 0. So f is continuous from the right at 0, and f is from the left at 1. At 1, it is continuous from the left, and at any point inside, it is continuous at that point. And f is continuous at c for c bigger than 0, less than 1. So from these three conditions, we can say f is conti on the interval 0, 1. So this is true. True. Okay. So distinguish between f continuous at a point and f continuous on an interval. Class number 6, intermediate value theorem. So we're going to abbreviate this as IVT, intermediate value theorem. It is one consequence of continuity. Okay. So what is the theorem? It is the following. So you will have to memorize the name and the statement of the theorem. It's the following. So if I have a continuous function on an interval a comma b, let's say. So let's say this is f of a and this is f of b. And f is continuous on the interval a comma b. Then f can go like this, right? So between fa and fb, you're going to pick any number L, intermediate value. Then you must be able to find C inside of this interval so that the value at C is L because of continuity. So that is intermediate value theorem. Okay, so let's write that down. If f is continuous on the interval and it is closed interval a comma b, I have to have fa and fb defined, so I should include a and b as the endpoints. So this closedness is important. Yeah. So f is continuous on the interval, closed interval a comma b, and L is any number between fa and fb. Then there between meaning L is between FA and FB, so FA not included, FB not included. Because I know that at A it is FA and at B it is FB, so they are not interesting. So I'm assuming that L is in between. Okay. Then there exists C such that C is inside, that means belongs to, is an element of, C is inside, strictly inside in this interval, because L is strictly between FA and FB. And f of C equals to L. The function value SC is L. That's intermediate value theorem. Memorize this. So for example, if f of x equals to this function, is there C such that f of C equals to minus square root of 3? So we want to do this analytically, that is without drawing the graphs. Okay, so this is a polynomial which is continuous everywhere. So observe that f is continuous on everywhere, so in the interval minus infinity, infinity. We want C such that f of C equals to minus square root of 3. So we need to achieve blank based upon blank. So since f is continuous everywhere on the real numbers, what we have to do is we have to find A and B such that if we call this number L, so minus square root of 3, we want to find C such that f of C equals to L. Therefore, we have to find two numbers A and B so that f of A and f of B, between these I have minus square root of 3. Okay, so by looking at this function f, it is clear that f at 0 is 10 and 10 is bigger than minus square root of 3, right? So can you find another number so that this number is less than minus square root of 3? Yeah, for example, if I plug in minus 20, big enough, then this number will be minus 8,000 and then plus 160 plus 10, so that will be a big negative number, so it will be less than minus square root of 3. So whatever that number is, I don't really care. Let's say that equal to star. So star is less than minus square root of 3. So at 0, it is 10. When x is 0, f of 0 is 10. And when f is minus square root of when f is minus 20, so when f is minus 20, f of b is less than minus square root of 3, so it is here. Okay, so there are two numbers. So because f is continuous, I don't care how it goes. I don't care. So since minus 20 is less than 0, let's call this A and let's call that B. So this number is f of A and that number is f of B. And minus square root of 3 is between f of A and f of b, and f is continuous. So we can utilize intermediate value theorem. So we need to achieve find a, b such that s dot t dot meaning such that minus 3 is between fa and fb. And based upon IVT, we can say the following. Number 1, f is continuous on the closed interval minus 20 comma 0. Because f is continuous everywhere on the real numbers, it will be continuous on this closed interval, of course. And then number 2, minus square root of 3 is bigger than f of minus 20 and less than f of 0. Right? So by IVT, there exists C in the open interval minus 20, 0. So this means there exists, this is in, there exists C in this open interval minus 20 comma 0 such that s dot t dot meaning such that f of c equals to minus square root of 3. So that's how you're going to justify the existence problem. Okay, so remember these steps. So there should be some c so that f of c is minus square root of 3. So the answer is yes. Yes. Another example. Does the equation sine x equals to 1 minus x have at least one solution? Why or why not? Again, we want to do this without drawing graphs, okay? So analytically. So I can change this problem as follows. I can say sine x minus 1 plus x equals to 0. And I can call the left-hand side as f of x. So, in other words, if I call that solution as c, right, then asking is there some c such that f of c equals to 0, where f of x equals to sine x minus 1 plus x. That's what this problem is asking, right? Well, I see that sine x is continuous everywhere. This is a polynomial continuous everywhere. If two functions are continuous, its sum is also continuous. So I know that f is conti on minus infinity, infinity for every real numbers. So all we have to do is we have to find a and b such that 0 is between f of a and f of b. Okay, so let's plug in some numbers. For example, if I plug in 0, then I get sine 0 minus 1 plus 0. Sine 0 is 0, so I get negative 1, which is less than 0. So we'll call this L. And now I need some number bigger than 0. Can you give me such input? If I plug in pi over 2, then I get sine pi over 2 minus 1 plus pi over 2. And sine pi over 2 is 1, so it cancels out. I get pi over 2, which is bigger than 0. Right? So if I draw a rough graph, if at 0, my value is something less than 0, at pi over 2, so that's 0, pi over 2, at pi over 2, something bigger than 0. So I don't know exactly how the graph go, but it must go through 0 because f is continuous, right? It may go like this, but anyway, it has to hit 0 at some point. So let's write exact steps. So 0 is my A and pi over 2 is my B. So let's write down the answer. So the solution answer is yes. Why? Because since f is conti on the closed interval 0, pi over 2, and f of 0 is less than 0 less than f of pi over 2. There exists c in the interval 0 pi over 2 such that 0 equal to f of c by IVT. That is, i.e., what was f? F was sine c minus, what was f? F is right here. So sine c minus 1 plus c equals to 0. So there exists c, so there is a solution, i.e. sine c minus 1 plus c is 0. Therefore, the equation sine x equal to 1 minus x has a solution. A solution meaning it could be more than one, but there's at least one solution.